cations are much smaller than their atoms because the same number of protons is pulling on less electrons. Here's the atom's radius. Here's the ion's radius. Notice the difference just by taking away one electron. Conversely, anions are much larger than their atoms because the same number of protons is pulling on more electrons. Here's the atom, 72 picometers. Here's the ion, 136. All I've done is add one electron to get F-. Ionic radii increase as we go down a group. So if I'm comparing these three ions here, from smallest to largest, the smallest would be lithium. It's closer to the top of the periodic table. And then sodium and potassium ion would be the largest of those three. As we go across a period, ionic radii decrease. For the cations, there's a large increase when we get to the anions, and then the anions decrease from left to right. Here's some examples in the third row on the periodic table. For isoelectronic ions, know the term isoelectronic, it means the same number of electrons. The larger the number of protons, the smaller the ion. If I'm comparing these three right here, if you look at the periodic table, they all have 10 electrons, so they're isoelectronic. The smallest would be magnesium because it has the most protons, and then sodium, and then fluoride. Ionization energy is the energy required to remove an electron. The higher the ionization energy, the more difficult it is to remove that electron. When we say ionization energy, we are referring to the removal of the first electron. There's also a second ionization energy, but we're comparing first ionization energy trends. There's a decrease in ionization energies as we go down a group. So here is group 1A. Here are the actual numbers. Notice there's a decrease as we go down. Cesium is the easiest one to remove an electron from. It's going to take less energy to remove cesium's electron. And that is because cesium is shielded from the positive pole of the nucleus by those inner shell electrons. And so those inner shell electrons shield the outer shell electron, and that outer electron is not held on as tightly. It's going to take less energy to remove that outer electron. There's a general increase as we move from left to right in terms of ionization energy. This is because effective nuclear charge increases from left to right. That means the nucleus is holding on to those electrons more tightly as we go from left to right. However, there are two exceptions to this trend, and I want you to know these two exceptions. The ionization energies for group 3A are lower than group 2A. That's one of the exceptions. And the other exception is the ionization energies for group 6A are lower than those for group 5A. And this is due to the relative stability. Group 2A is relatively stable. It's got a full S subshell. And group 5A is relatively stable. It's got a half-filled P subshell. Now the noble gases have the largest ionization energies because they have a filled S and P subshell, so they are very stable. They do not want to lose an electron. Here are some examples as we go across sodium's row. And what I want you to notice are the two exceptions. The exceptions occur between groups 2 and 3A, so in this case between magnesium and aluminum, and 5A and 6A, in this case between phosphorus and sulfur. If you look at the other trends, there's a general increase, but in these two cases there's a decrease, and I will hold you to these two exceptions. So let's look at an example here. Put these in order from largest to smallest. In this first one here, these are all in group 4A. The largest ionization energy is the one closer to the top of the periodic table, Si, and then Ge, and then finally lead has the smallest. It's going to be easier to remove lead's electron. It's going to take less energy to remove lead's valence electron. In this example here, all of these elements are in the same row. Let me put these in order for you from largest to smallest. And then I will show you where the exceptions occur. The exceptions occur between groups 2A and 3A and between groups 5A and 6A. So that's where the exceptions are. I've underlined them. And you can go back and look at the periodic table and see where those exceptions occur. Electron affinity is the energy change when an electron is accepted by an atom. So this is opposite of ionization energy. For most atoms, energy is released, so you have a negative value here. The pattern is not very evident. Here are some examples. We're not going to worry about trends in electron affinity because the pattern is not very evident. And the final trend is electronegativity. Electronegativity is the ability of an atom to attract toward itself electrons in a chemical bond. We'll look at chemical bonding a little bit later, but when we draw Lewis structures, electronegativity is a measure of which atom wants these electrons that I've circled more. In this case, does hydrogen want them more, or does fluorine want those electrons more? Well, fluorine is the element with the largest electronegativity, a value of 4.0. The trend, electronegativity increases as we go from left to right and decreases as we go down a group. So let's look at some examples. Put these in order from smallest to largest. Now with electronegativity, the largest value is F. So I want to find the element that is closest to F that will have the largest value for electronegativity. So if I look at this first example, from smallest to largest, the smallest would be Ru. It's furthest from F. And then In. And then finally 10 would have the largest value for electronegativity because it's closest to F. Let's look at the next example. The smallest value would be Si. Next would come P. Now if you look at your periodic table and you compare N to Br, they're the same distance from F. I know one's in the same row, one's in the same group, but they're the same distance from F. So relatively, I would say those two have the same value for electronegativity. So the trend top to bottom, left to right, which matters more? In this case, it's whichever element is closest to F has the highest value. And I would say nitrogen and bromine, since they're the same distance, would have relatively the same value for electronegativity. And then this last one here, the smallest value, again, furthest from F would be Pb. And then As. And then if I look at carbon and iodine, again, you'll notice they're the same distance from F. So I would say those two are relatively equal in terms of electronegativity.